Hello guys, in this video I'm going to show you an example of how to apply the law of conservation of energy in AC circuits. Okay, basically this law is saying that whatever energy you produce from your sources will be consumed in your elements. Okay, uh, in AC sources, it's a little bit different, but with same concept. Okay, because we have two kinds of energies. We have like the actual power consumption, which is consumed, which we call B average, for example, average power. And we have also what's called the reactive power, okay, which is not consumed, it's stored. So the capacitor and the inductor doesn't consume power. They are not consuming any power, okay? But they store the power in some form of energy, like for example, electromagnetic energy, okay, or static charge, and they like constantly exchanges power with the sources. Okay, so they take the power, like for example, store the charges in the capacitor, and then some time later it discharges the charges again to the source, and so on. Okay. Okay, so we need to show how this law of conservation of energy is happening in AC circuits. Okay, and the best way to do that, as usual, using an example. Okay, so this example, I choose this example because it's very similar to the examples you have in your homework. This example is problem B 825. Your homework is 822, just like 3 blocks away. Okay, but it's very similar. Okay, so let's see how to do that. Okay, so to find actually the power, either actual power or reactive power, we should know like the laws, from which we can determine these powers. And based on these laws, we're gonna know what we should determine in this circuit in order to solve or find the powers. Okay, so they are not like complicated, actually very simple. Okay, so for any resistance or resistances, the power is called the average, and it's equal to half the magnitude of the current that pass through. So if we have like a resistance like that, and it has a current like that, okay, so it's half the magnitude or the amplitude square of the current multiplied by the resistance. Okay. And by the way, let's like dig into what is this I. So let's assume we have an I of t equal to, for example, Im sine omega t plus theta. Okay. So this I here is actually Im. Okay. So, and when you divide Im by square root of 2, this is called IRMS, the root mean square value. Root mean square value of that current. Okay. And the definition of the root mean square value of a current, it is basically the equivalent DC current of that AC signal that will produce the same heat in the resistance that it's passed through. Okay. So we can write it in another way. We can write it as I square RMS R. Okay. So if it's given as R, if the current is given as in RMS directly, you can just apply this law here. If it's given usually like amplitudes, then you apply the first one. Okay, that's the power and the resistance. The power, the reactive power now. The reactive power in capacitors or inductors. Okay, we're gonna call it Q. So QC, for example, for capacitance, will be equal to half, again, the amplitude of the current square that pass through the capacitor multiplied by the XC. For example, minus J, XC might be like, for example, minus J 5, whatever, okay? And you see here something, that this value is imaginary. Pure imaginary. Let's write it as pure imaginary. Pure imaginary value. It has no real. So any complex number is x plus gy. Okay? QC is always gy. It always has j. There is no real part. And B average, on the other hand, it's always pure real number. There is no j. It's always x. Okay? Good. Finally, the reactive power in inductor is very similar. It's also reactive power. Let's call it QL. It's equal to half the current pass through the inductor square, the amplitude of it, multiplied by XL. And again, it is pure imaginary value. It has no real part. It's a complex number that always have like the imaginary part, the gy. Okay, either positive or negative, whatever. Good. So looks like to find the powers on all these elements, okay, these passive elements, okay, either inductor, resistance, or like capacitor, all of these are called the passive elements. Passive elements. So to find them, you have to find the current. So basically, we have to solve the circuit. Okay. So here is our circuit here. Okay. The current is given. It is 0.3 angle 30. And the voltage Vs is also given. It's a 20 volt. It has no phase. The phase is 0. Okay. R is 100. R1 is 100. R2 is also 100 ohms. ZC is minus J50. It's given. And ZL is J50. It's also given. Everything is given. Okay. So looks like the best way to solve this circuit is to use the nodal analysis. So we have here 3 nodes. We have, let's call, for example, V1. Another node here, V2. And another node here. But we know in nodal analysis, we usually choose one of them and make it ground. And usually we choose the one in the bottom. Can you use anyone? Yes, you can choose this one for V1 as you know, the ground. That's up to you. Okay. So we're gonna choose this one here in the bottom as our ground. Okay, and let's solve the circuit. So I'm gonna assume the current directions here, and this is very important. I'm gonna explain why at the end. Okay, so I'm gonna assume the current is a pass through the source Vs I1, or basically R1 as well, and the current that pass through ZL IL, the current that pass through the CIC, that way. I'm gonna assume the current that passes through R2 I2, and this current has its own name, Mr. IS. You don't need to assume it. Okay, let's go back to our normal code. So using nodal analysis, add V1 and V2. Okay, so add V1. At V1 node, you have all the currents are going out. So I1 plus IC plus IL equal to 0. I1 plus IL plus IC equal to 0. Okay. What is I1? I1 is going from V1 to this point here, okay, which is Vs, because this is 0. Remember, this is 0, okay, and the voltage difference between across the battery is the voltage of the battery. So this is 0. This minus this one minus this one should be equal to Vs. This is 0, so this should be Vs. That here is 0. So the current is equal, I1 here is equal to V1 minus Vs divided by resistance 100 ohm. IN. IN is much easier because the second node here is 0. And it goes from V1 to the ground. So it's V1 minus the ground minus 0 over ZL. So V1 minus 0, so it's 1 divided by ZL, which is J50. J50 equal IC. IC is going from V1 to V2. So it's V1 minus V2 over ZC. V1 minus V2 over ZC. ZC is minus J50. Minus J50. And all of this is equal to C. Let's simplify this one. So V1 over 100 minus Vs. Vs is 20 over 100 plus V1 over G50 plus V1 over minus G50 minus V2 over minus G50 equal to 0. Good. One thing we notice here, this is V1 over G50, and this is V1 over minus G50. So it's minus V1 over G50. So this guy will go with this guy. And this is minus and minus, minus V2 over minus G50. So this will be positive. The minus will cancel the minus. Okay. And we can bring this constant to this side here. So the equation will be like that. V1 over 100 plus V2 over G50 equal to 20 over 100 is basically 0 will go to 0.2. This is my number one. This is equation one. Equation. We can write it in this way. 0.01 V1 plus 1 over G50 is actually minus 0.02 J2 equal to 0.2. Okay, let's here like that very quick. Yeah, it should be okay. Okay. So that's number one. That's the question. Now let's do the Kirchhoff current law at node V2 this time. Number two, at V2 node. At V2 node, we have IC going in, IS is going in, I2 is going out. So IC plus IS minus I2 equal to 0. IC plus IS minus I2 equal to 0. IC, we have it already. It's V1 minus V2 over minus G50. V1 minus V2 over minus G50. IS is given is 0.3 angle 30, 0.3 angle 30, which looks ugly here because we have a rectangle form. Anyways, we can convert it. Minus I2, which is V2 over 100. V2 over 100. V2 minus 0 over 100. Equal to, this is minus. Yes, this is minus, no positive. That's a big mistake. Okay. So let's simplify this. 0.3 angle 30, we can convert it. If you convert it using our calculator, you know, it will be 0.26 plus 0.15 J. Okay. Good. So we can keep point 3 angle 30 on that side and bring that guy and that guy to the right hand side. Okay, so that will be uh, minus 0.02 V1. Okay, then plus V2, and V2 will be 1 over 100, which is 0.01, minus, not minus 1 over J50, that will be positive, so it will be yeah, let's do it one by one, not to make any mistake. So this will be V1 minus V2 over G50. We go to the next, so the right hand side, so the minus G50 will be positive G50 plus V2 over 100 equal to 0.26 plus 0.15 J. Okay, so we're gonna have here V1 over G50 plus V2, and we're gonna have 1 over 100 minus 1 over J50 equal to 0.26 plus 1.5 J. Okay, good. So okay, what we should do? We should simplify this. So let's simplify it. So I'm gonna have it here. So where is the calculator, guys? Calculator. Yes. Okay. Let's bring that. So we need 1 over G50 first. 1 over and both parentheses 50i. That will be minus 2 minus O2i. So that minus I J V1. So V1 multiplied by this guy plus V2. 1 over 100. Okay. 1 over 100. 1 is and we have V 1 minus 1 over G50. 1 over and put another parentheses. This is very important. 50i. Okay. Calculate that. 0.01, 0.02. 0.01 plus 0.2 J. And the right hand side is still the same, J50. Okay, so that's number 2. So we have now the 2 equations. So we can now use the other tool, the online tool that we have, that we learned. Okay, and solve these 2 equations together. So we have, I believe I have it already. So let's see, let's check. I believe I have it already. So yeah, I believe I have it. So let's see. 0.01 and there is no imaginary. That's right. This x1 is v1 here. Yes, there is no real for v2, but there is minus 0.02 for the imaginary part, and the real part, I'm sorry, the constant is 0.2, and there is no imaginary. Now, this is just I switched the signs, so it's okay. So it's not a problem. So here v1 is negative, but here is v1 is positive. Okay. Here V2, look, it's all positive. Here it's all negative. That's fine as well. That should be switched, and yes, it's a switch. Okay, but yeah, we can do it. We can if you have like a doubt. Let's do what we have. Basically are the same, but just multiply this by minus. It's fine. It'll be the same. So let's now update the equations, update coefficients, solve the system. Exactly the same solution. I know the solution. Exactly the same solution. Okay. So what we have here, what we get? So we get like V1 equal to 4.62 plus J16.55, which is in polar 4, yeah, 17.18, angle 74.4. Okay, that's basically V1. Now V2. V2 in polar 4 directly 11.29, angle 42.89, and as a rectangular form, which is the one that we're going to use, 827 plus J 7.6. No, it's very like tedious, you know. I know, but this is basically the nature of these examples. These problems in AC circuits is very tedious. Long calculation. That's why you have to use these online calculators. Otherwise, your life would be hell, you know. Anyways, so we get V1 and V2. Okay. Is this our target? No, by the way. Our target is to find the currents. Why? Because these, by the way, there are like other we can derive other formulas for the reactive power and the active power using the voltage, but that's fine. Let's use the current. So I will not like calculate the current. I use the basically the like a calculator to solve it, but I'm gonna give you the final answers. So I1 basically, I1 is the one that flows into R1 here. It's V1 minus 20 over R1. So I'm gonna write also so V1 minus 20 over R1. And we get V1 here. We know V1 now, and we know R1 is 100, and the 20 is a constant. So that will be, if you solve that, so it will be minus 0.154 plus 0.165J, or in polar form 23, 132.9. Okay. IC will be equal to, IC is actually V1 minus V2 over ZC. V1 minus V2 over ZC. So it's equal, if we have V1 now and V2, and VCC is known, minus G50. So if you do that, it's minus 0.177 minus 0.73J, or in polar form 0.192 minus 157.5. Okay. Now I2 is simple. I2 is believe V2 over R2. V2 over R2 here. So it's V2 over R2. R2 is 100. V2 is known now after solving the equation. So that will be 0.083 plus J 0.077 or 0.113 angle 42.9. Finally, IL. IL is the current flowing through the ZL. It's also simple, V1 over V1. V1 is known now over ZL. If you solve that using the online calculator, we learned 0.33 minus, of course, this is approximations, okay, minus 0.092 J, or in polar form 0.344. Yep. Angle minus 15.6. Okay, we get all the currents. Okay, now how we find the reactive and active? We're gonna start first, as he said, by the passive elements. We have four passive elements. We have R1 is a passive element. We have R2, we have ZC, and we have Z. Okay, and we know the equation is here. Okay, so let's get number one, the active power in R1, which we can call B average one. It's equal to half I1 amplitude square R1. Okay, and here is why we have to get like the polar form, because I1 is actually the polar form. So this one, 0.23. Okay, you don't have, you should have just this in your mind. Okay, because you have the polar form. So it's half 0.23 square, and R1 is 100. If you do this calculation, that should be 2.645 watts. Of course, you might not get exactly 6 point, maybe 2.64. You might get like 2.55, because again, the nature of these like complex, really complex problems, complex calculations, you're gonna have rounding. You're gonna have like maybe 0.1 difference, okay, something like that. So you should accept that. Should be close, basically. Okay. Okay. Number two, another active power. Active power in R2. The active power is only in the resistances. Okay. B average 2 half. What is the current flowing in R2? It's I2. We call it I2. So half I2 amplitude square R2. So it's half. And again, the importance of the polar form. I2 amplitude is basically the amplitude here. So this is I2, so it's 0.113. 0.113 square, and again R2 is 100, like R1. That will be 0.638 watts. Number three, now we have four. We have two resistances and an inductor and a capacitor. So the other two are reactive powers. So the reactive power in the capacitor C. So we're gonna call it QC. QC is half again the amplitude of IC square, the current through the capacitor, which we call IC by the way, multiplied by XC. So half, where is IC? Mr. IC is here. That's the amplitude. So 0.192 square, and what was XC? Minus J50. Minus J50. Look, guys, we said in the beginning that the active powers should be real all the time, real, pure real. That's what we have here. Look, real numbers, 2.6, 0.638. There is no J, there is no imaginary. Okay. And we said that the reactive powers should be pure imaginary. Look, this is constant, will multiply by 50 or minus 50, and you have the J. So it will be equal to, let's calculate it. So QC is minus 0.9216, pure imaginary. There is no real part. Okay. Number four, the reactive power in the inductor L, QL, half IL amplitude square XL. Very simple. Half, where is Mr. IL? Here is IL, that guy. What's his amplitude? 0.344 square multiplied by J50, the XL. It's given in the question. And again, it's pure imaginary. How much is this one? 2.958 J, pure imaginary. Okay. Good. We calculated, this basically is the first requirement in that question. We calculated the four powers consumption, for the complex power, we can say, in the four passive elements. Okay. Then calculate for each two sources. Oh, we didn't touch upon that. I showed here only how to calculate the power in the passive elements, resistance or inductor or a capacitor. I didn't show you how to find the power through like a source. Okay, it's also simple. It's also simple. If you have like a source like that, it's called voltage source. Let's first start by a voltage source. Okay, but this is very important. If you assume the current like that, let's assume the current is called I, then the power of this source, let's call it S. Okay, S is for the source power. SVS, the source of that, the power of that VS, the complex power of that source VS is equal to. It's very important. If you assume the current is going like that, so it's minus VS, minus half first, I'm sorry, half VS and I conjugate. What is I conjugate before we continue? Or if I, for example, is equal to x plus gy, if I conjugate, I asterisk is x minus gy. You should only flip the sign of the imaginary part. Only the sign of the imaginary part. Keep the sign of the, so if the x is minus, keep it minus. If it's positive, keep it positive. If the imaginary part was positive, make it minus. If it was not minus, make it positive. But look at that. This minus here because the current is going out of the positive terminal, okay, or going into the negative, whatever, the negative terminal. Now, if you assume the current is like that, that's VS, and the current is going into, so in that case, SVS is equal to half. There is, I'm sorry, this is minus here. Here there is no minus, half VS I conjugate. But look now, the current is going into the positive terminal. Okay, with that we should make it positive. That's very important, very important. Okay, because here, if you look, guys, there are two questions. There are two in this problem and the problem 8. It's all based on you how to assume the current in the resistance R1. So in the solution of the book, they sometimes make it like going into like moving like that, or sometimes like that, and this will change like how the formula to calculate the reactive power in the source. That's very important. Okay, otherwise you will not prove the conservation of energy. You will find that the energy is not conservative. Okay, good. For the current source, again, same observation. So if we have a current source like that, IS, so S IS, and there is a voltage like that, again, positive, negative. In that way, it's minus half, let's call the voltage V, V, and IS conjugate. Okay. If you assume it like that, same as voltage source. Now, negative volt, positive, and it's going down. I mean, if they are in the same direction, it's a negative. If they are opposite, so SIS in that case will be positive, half VIS. Okay, that's basically how we calculate like the. Okay, so we have now the formulas for like the sources. So let's see which one of the four, this 1, 2, 3, 4 formulas we should apply in our cases. So let's check first the VS. For VS, oh yeah, VS, the current is going into the positive, going into the positive, going into the positive. So we should apply this one. Let's do it. So S VS equal to half, there is no minus, VS is 20, and the I is actually, which I? This is I1. So we need I1 conjugate. So we need this one. So let's copy and paste. That's much faster. Copy this. Should copy. Hopefully. Yes. Okay. I'm gonna put parentheses. But remember the conjugate. So we're gonna flip the sign of the imaginary part. So we're gonna put minus here. Okay, let's review. By one, yes. Okay. So this is simple to do. So 2, this will be 10. So this will be equal to minus 1, 5.54 minus 1.65J. Okay, that's SVS, very simple. Now, let's go to the current source. Which one we're gonna apply? We're gonna apply this one or this one? We don't know. Let's go and see. So IS is going up like that. And what is the voltage across IS? Basically V2, and the V2 is like that. Okay? We assume this is the positive reference to the ground here. So the ground is negative. And the direction of the voltage from the negative to the positive. So they are in the same direction. Let's see which one we're gonna apply. Same direction, we're gonna apply this one. So IS equal to minus half V, and in that case it's V2. I'm sorry, not V1. Yeah, V2, not V2. You see V2. So where is Mr. V2? That's Mr. V2. Let's copy V2. That's V2. I'm gonna copy it. Copy Mr. V2. Paste it. And put parentheses. Then I conjugate. Okay. We have I in both for polar and rectangle. Look, it is 0.3 angle 30. So the conjugate will be 0.3 angle minus 30. That's if you want to do the conjugate on the polar form, but we like always the rectangle because we're gonna use the calculator. So we already did the conversion, and I was what is it? Yeah, 0.26, 0.15, 0.26, 0.15, 0.26, 0.15 J. Both were positive, but now we need I conjugate, IS conjugate, so we're gonna flip the sign of the imaginary part. Okay, and if you, I'm sorry, here is J here, G7.6. And if you do the like this multiplication, this will be minus 1.65 minus 0.38 J. Okay, I'm gonna put this into rectangles. Okay, now in our circuits, we have a generated power and we have generally a consumed or stored power. Okay, in AC circuit, the generated power will be equal to the stored and consumed power. The stored power is basically B average, which we calculate in the resistances. These two active power, and the stored power will be the reactive ones, QC and Q. Okay, where is the generated powers? SVS and SIS. And that means if you add them together, you should have zero. Okay, you should have zero. Remember, we have real part and we have imaginary part. When we do the 4 elements, the resistance is there will always pure real part, and the reactances, the reactive power, have always imaginary part. The source have both. You have real and you have imaginary. Real and why? Because this is the source. This is the one that generates the active power and the reactive power. Okay, so if we want to know the total reactive power that input to the circuit, just add the imaginary part of SVS and SIS. So the total reactive power QT generated. Let's write generated let's call it Q total equal to minus 165, which comes from J, of course, which comes from SVS, minus 0.38J, which comes from SIS. You take it with its sign. It's a sign, whatever, positive, negative, whatever it is. Okay. So looks like the total generated. Let's add them together. I think I really add them together here. It is minus 203J. Now, if we added QC and QL, it should give us the same number. Let's do that. QC plus QL equal to QC is minus 9216.9216 J. QL is plus, it's positive, 2.958. 2.958. Let's add them together. I believe also I added them together before. It is 2 positive 20364J. Now, if you add Q total generated plus QC plus QL, it's almost zero. That's conservation of the reactive or stored power. Let's do the same for the active power. So the total, that's number one here. Number two, the total active power generated, let's call it B total. It should be the addition of the real part of the SVS and SIS. So it's minus 154 minus 165. I believe I added them before. That's basically 3.19 minus 3.19. Now, if I added B average 1 or R1 plus B average 2, let's do that. It should give also 3.19. So it's 2.649, 2.649, 2.649 plus 0.638, 0.638. If you add these together, it's 3.283. Okay, and you will never get this exactly the same, but it's very close as you see, 3.19, 3.228. Okay, it's 0.1 difference. So Q, I'm sorry, not Q now, B total plus B average 1 plus B average 2, almost 0. That's what is that one? Conservation of active power. Meaning the total active power generated is the total active power consumed in the resistance. So one final note here, although the Q's, QC or QL might be positive or negative, but B average must be positive, must be. It has to be positive, okay? It has to be positive all the time. Anyways, so that's it, guys. We see in this example, you know, how basic to solve it first, how we apply, how we find the active power and active power, basically the complex power, and how the generated active and reactive power is equal to the stored reactive and consumed active power is circuit. Okay, guys, thank you very much, and see you in another video. Bye-bye.